In January 2026, two men looked at the same NASA data and said opposite things out loud. One was the administrator of NASA. He said he had full confidence in the Orion heat shield. The other was a former space shuttle astronaut and engineer. He said flying it was the same reasoning that killed the crews of Challenger and Columbia. Both men had seen the reports. Neither was lying. And 11 weeks later, 4 people climbed into that spacecraft anyway. Here is what they were arguing about. In November 2022, the Artemis I capsule returned from the moon, and its heat shield did not erode the way it was supposed to. Instead of charring evenly, it cracked and shed in chunks. NASA spent 2 years working out the cause, and the answer was that gas had been building up inside the material with nowhere to go. By then, the shield for the next flight was already built, already installed, and could not be replaced. So NASA changed the only thing left that it could change, not the spacecraft, the way it would fall. Artemis II had come home by skipping off the top of the atmosphere, like a stone across water, to bleed off speed gently. Gently turned out to be the problem. So Artemis II came in steeper and hotter and stayed hotter for longer, on purpose. 9 days before that fall through the atmosphere, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen lifted off from Launch Complex 39B. They became the first humans to leave low Earth orbit in more than 53 years. They went farther from home than anyone in history, 252,756 miles. And they reached that farthest point in radio silence behind the moon, where nobody could hear it happen. They watched a total solar eclipse that lasted the better part of an hour. They suggested names for 2 craters nobody had ever named. And every one of those 9 days ended in the same place, falling toward a question the ground could not answer for them. This is the story of those 9 days and of the decision underneath them. The rocket that carried 4 people to the moon in 2026 had flown exactly once before, and there was nobody on board. Its first time were instrumented mannequins, wired to measure how much radiation a human body would absorb on the way out and back. That is not a criticism, it is the design. NASA called Artemis II a test flight and meant it literally. The Space Launch System had launched 1 mission in November 2022. The Orion capsule had flown twice, both times empty. Every major system on that stack had worked. Not one of them had ever worked with a person's life resting on it. On April 1st, 2026, that changed. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen walked out to Launch Complex 39B and climbed into a spacecraft no human had ever ridden. Wiseman commanded. Glover flew as pilot. Koch and Hansen were mission specialists, and Hansen was the outlier in a way that mattered to 2 countries at once. He is an astronaut of the Canadian Space Agency, and no non-American had ever been assigned to a flight beyond low Earth orbit. 24 people had traveled to the moon before this crew. All 24 were American men. Getting them to that pad took longer than anyone wanted. The stack rolled out of the vehicle assembly building on the 17th of January, riding a crawler transporter at a walking pace slower than a walking pace. 4.5 million pounds of rocket moving at less than a mile an hour, taking most of a night to travel 4 miles. The first launch attempt was scheduled for early February. It did not happen. An unusual cold snap pushed into Florida, and NASA does not launch cryogenic rockets into strong winds and freezing temperatures if it can wait. February 6th slipped to February 8th. Then, the wet dress rehearsal, the full practice countdown where the vehicle is loaded with propellant and taken to within seconds of ignition, found a hydrogen leak. Then, a helium flow issue. Each one on its own was small. Together, they cost 2 months. This is worth sitting with because it is the part of spaceflight that never makes a thumbnail. Liquid hydrogen is the smallest molecule there is. It leaks through joints that would hold anything else. Every rocket that has ever flown on hydrogen has fought it, including the space shuttle, which scrubbed for the same reason more than once. There is no clever fix. There is only finding it, tightening it, and loading again. On the 12th of March, NASA held the Flight Readiness Review and came out of it with a set of launch dates. Not a launch date, a set. 7 opportunities, April 1st through 5th, and then one on the 30th. Look at that gap. 6 chances in 6 days, then nothing for more than 3 weeks. That is not scheduling, that is orbital mechanics, and it is the first genuinely strange thing about this mission. A trip to the moon is not a straight line to a fixed target. The moon moves around the Earth once every 27 days or so, and its orbit is tilted and the Earth is turning underneath the launch site. To fly the specific path NASA wanted, the moon had to be in a specific place at a specific time relative to a rocket leaving Florida. Miss that arrangement and you do not lose a day, you lose a month until the geometry comes back around. And the path NASA wanted was not chosen for convenience. It was chosen because it costs almost no fuel, and because if the engines failed at any point, the moon's own gravity would sling the spacecraft back toward Earth without anyone having to do anything. So the launch windows were not a scheduling detail. They were a consequence of the safest possible route. And because that route depended exactly where the moon sat in early April, the date on the calendar was quietly deciding things nobody in the control room was thinking about yet. It was deciding how far from Earth this crew would get. It was deciding what they would see. April 1st arrived clear. Call to stations went out in the late afternoon. The countdown ran clean, which after February felt almost suspicious. At 6:35 Eastern Time, the 2 solid rocket boosters lit. 8.8 million pounds of thrust came off that pad. For context, a fully loaded Boeing 747 weighs about 970,000 pounds. The Space Launch System left the ground, pushing roughly 9 of them upward at once. 2 minutes in, the boosters burned out and fell away. Around 8 minutes, the 4 engines on the core stage shut down and the stage separated, leaving the upper stage and Orion coasting. Then, 4 wings unfolded from the European service module and locked into place, each one beginning to draw power. Fully extended, they gave the spacecraft a span of about 63 feet, wider than the wingspan of a small airliner, and they carried cameras that would matter enormously later. Orion was in orbit, and NASA later described the insertion as pinpoint. Here's the payoff, and it is not the launch. Every crewed flight since 1972 had gone up to a place a few hundred miles overhead, where you can come home in under an hour if something breaks. Artemis II was about to leave that zone permanently for 9 days. Once the upper stage fired again, there would be no aborting to a landing site. There would only be the trajectory and the moon at the far end of it, and the physics of the figure 8 bringing them back. The spacecraft had a name by then. The crew had called it Integrity. About 3 hours after launch, with the moon still 4 days away, the crew took manual control and flew Integrity in formation with the spent rocket stage that had just carried them. Nothing was docking. There was nothing to dock to. So the obvious question is why NASA spent some of the most expensive minutes in spaceflight practicing a maneuver against a piece of hardware it was about to throw away. 3 hours after leaving Florida, Reed Wiseman took the hand controller and began flying a spacecraft toward a piece of dead metal on purpose. The target was the interim cryogenic propulsion stage, the upper stage that had just fired to push Orion toward the moon and then separated. It was inert. It had no thrusters, no guidance, nothing to grab onto. Within days, it would be on its own path around the sun and nobody would ever touch it again. And for roughly the next hour, the crew flew relative to it by hand. This is the chapter's central idea, and it is worth stating plainly because it explains a decision that looks wasteful. Orion has never docked with anything, not once, in 3 flights. Every future mission in the Artemis program depends on it docking with something, and the only way to find out how a spacecraft handles in a manual close approach is to try it in deep space with the actual vehicle and see whether the way it responds matches the way the simulators said it would. The crew had flown this maneuver thousands of times in Houston. Simulators are built from mathematical models of how a spacecraft's thrusters push it around. Those models are educated predictions. They are validated on the ground, in a building, on Earth, where nothing behaves quite the way it does when the whole vehicle is loose in vacuum with propellant sloshing in half-empty tanks. So Wiseman and Glover pushed the controller and watched what the ship did. Think about what that actually asks of a person. There is no air resistance to slow anything down. Nudge the spacecraft toward the target, and it keeps moving toward the target forever until you nudge it back. Every correction you make is a new problem you have created for yourself 30 seconds from now. Astronauts describe close-in flying in orbit as counterintuitive in a way that never fully goes away, because the instincts you built driving a car or flying an airplane are actively wrong. And here is why any of it matters. Under the current Artemis plan, no Orion ever lands on the moon. Orion carries the crew out and brings them home. Something else lands. That something else is a commercial lunar lander built by SpaceX or Blue Origin, launched separately, waiting in space. The crew rides Orion to it, transfers across, goes down, comes back up, transfers back, and rides Orion home. If Orion cannot rendezvous and dock, the entire architecture stops. Not delayed, stopped. Which is why NASA spent an hour of a 9-day mission flying formation with garbage. It was the first real data on whether a spacecraft that has to do the hardest job in the program can be flown by hand at all. Now the vehicle itself, because the rest of this story does not make sense without knowing what Orion is. It is two pieces bolted together. The crew module is the cone, the part that comes home, roughly 16.5 feet across at its base. Inside is a pressurized volume smaller than most people expect. 4 adults, their seats, their equipment, and enough room to move past each other if they are polite about it. Behind it sits the European service module, and that is the part that is not American. It carries the propellant, the main engine, the oxygen, the water, and the power. It's built by the European Space Agency and Airbus, and Orion cannot function without it. It's also the part that gets discarded before re-entry, burning up in the atmosphere while the crew module falls the rest of the way alone. 4 solar array wings extend from it. Fully deployed, they span about 63 feet. They rotate to track the sun. They fold to protect themselves during engine burns, and each one carries a camera looking back at the spacecraft. Those cameras were not installed for the view. They exist because Orion has a problem every spacecraft has and almost none can solve. Once you're in flight, you cannot see your own vehicle. You have telemetry, you have sensors, you have numbers on a screen, and you have no way to simply look at the outside of the thing you're sitting in. Orion 1 had come home with damage nobody knew about until the capsule was on a ship. So NASA put cameras on the ends of the solar arrays pointed inward so engineers on the ground could inspect their own spacecraft from outside while it was still flying. They were an inspection tool. Nobody planned for what they would end up recording on the 6th of April. There's a third layer to the ship that almost nobody discusses. The heat shield covers the blunt base, and it gets all the attention. But the sides and the upper cone are protected too by ceramic tiles related to the ones the space shuttle wore. During re-entry, the base takes the worst of it, and the back shell takes what wraps around. By the second day, the crew were in a rhythm, working in shifts, sleeping in shifts, running through the checklist of tests that were the actual reason for the flight. Life support, thermal control, communications at increasing distance, radiation monitoring, the effects of 9 days in deep space on 4 human bodies. A test flight is mostly bookkeeping performed at enormous expense. And somewhere in the first days, they gave the spacecraft its name, Integrity. It's an unusual choice. Spacecraft names lean heroic or mythological. Apollo capsules were Columbia, Eagle, Odyssey, Endeavour. Integrity is not a heroic word. It's an engineering one and an ethical one at the same time, and both meanings apply to this flight with uncomfortable precision. Structural integrity is whether a thing holds together under load. That was in the most literal sense the open question hanging over the entire mission. And the other kind of integrity, the kind that describes whether an institution tells itself the truth about its own data, was exactly what NASA had been publicly accused of lacking 3 months before launch. The crew almost certainly did not intend the second meaning, but they flew a capsule called Integrity through a re-entry that a former astronaut said NASA did not understand well enough to attempt. When the helicopters brought the crew to the recovery ship 9 days later, the call that went out over the deck was Integrity incoming. Everything on this spacecraft had a backup. 2 flight computers, redundant thrusters, multiple communication paths, layers of contingency stacked on layers of contingency. One system did not, could not, and never will. And it was the one that had already failed once. The bottom of the Orion capsule is 16.5 feet of material designed to destroy itself. That is not a flaw. That is the entire idea. And if it stops destroying itself at the right rate, everyone inside dies. The material is called Abcoat. It is a mixture of silica fibers in an epoxy binder, and it is not new. Something very close to it protected the Apollo command modules coming back from the moon in the 1960s. NASA went back to it for Orion for a straightforward reason. It is the only ablator with a track record of bringing humans home from lunar distance, and lunar distance is the hard case. Here is why lunar distance is the hard case, and it comes down to one number. A spacecraft returning from the International Space Station hits the atmosphere at roughly 17,000 miles an hour. A spacecraft returning from the moon hits it at nearly 25,000. That sounds like a difference of about 40%. It is not. The energy a vehicle has to shed is scales with the square of its speed, so the actual heating load is roughly double. Every crewed spacecraft flying today comes home from low Earth orbit. Orion is the only one built for the other number. Around 5,000 degrees Fahrenheit, hot enough to melt the titanium skeleton and carbon fiber skin of the capsule several times over, if any of it were exposed. Which is why the shield does something clever. It burns. Ablation works by sacrifice. The outer layer of Abcoat chars, breaks down, turns partly to gas and peels off into the airflow, and every molecule that leaves carries heat away with it. The material is not resisting the heat, it is spending itself to carry the heat somewhere else. A shield that came home pristine would be a shield that had failed, because it would mean the heat went into the spacecraft instead. What matters is that it burns evenly, at a predicted rate, in a controlled way. Smooth erosion, layered by layer, like a candle rather than a firework. On the 11th of December 2022, the Artemis I capsule came down in the Pacific after 25 days in space, having flown around the moon with nobody on board. The mission was declared a success. The primary objective of that entire flight, stated openly beforehand, had been to prove the heat shield. Then engineers looked at it. The surface was not smoothly eroded, it was cratered. Cavities where chunks had broken away, cracks running through the char. In more than 100 locations, the material had not burned off, it had let go. The Orion program manager first mentioned it publicly in March of 2023, describing more variation across the shield than expected, and material that ablated differently than the computer models and ground testing had predicted. The photographs did not become widely available until the agency's own Inspector General published them in a report in 2024. NASA spent roughly 2 years on the investigation, and this is what it concluded. Abcoat produces gas as it chars. That is normal and expected, part of how ablation carries heat away. But the gas has to be able to escape through the material, and the Abcoat used on Artemis I was not permeable enough to let it. so the gas had nowhere to go. Pressure built up inside the shield, underneath the charred outer layer, and eventually it pushed that layer off in pieces. The shield did not fail because it got too hot. It failed because in places it did not get hot enough for long enough. The evidence came from testing the material on the ground in an arc jet, a facility that fires superheated gas at a sample to reproduce re-entry conditions. Investigators found they could recreate the same cracking and shedding, and they found something that pointed straight at the cause. The permeable sections of the Artemis I shield had not suffered the same char loss as the less permeable sections. Same flight, same trajectory, same heat, different permeability, different outcome. And the trajectory turned out to be a major contributor. Artemis I had flown a skip entry, dipping into the upper atmosphere to shed speed, then rising back up briefly before making its final descent, like skipping a stone. It's a genuinely good technique. It gives you precision about where you land, and it spreads the heating out instead of taking it all at once. But during the skip, up in the thin part between the dips, the heating rate dropped. Less heat meant less charring at the surface, while the material underneath kept cooking and kept producing gas. So the gas production stayed high, while the escape route stayed closed. Pressure accumulated in exactly the window where the shield looked, from the outside, like it was having an easy time. Apollo used skip entries too, and Apollo's heat shields came home intact. The difference is that the abcoat for Artemis I had been changed slightly from the original, and the change affected its permeability. Now, hold two dates next to each other. The heat shield for Artemis II was installed on its capsule on the 25th of June 2023. That's 3 months after the problem was first publicly acknowledged, and well over a year before the investigation reached its conclusion. The shield that would carry the first crew was already bolted on before anyone knew why the last one had come apart. It was made from the same abcoat, applied in the same way, with the same permeability characteristics. NASA has been direct about this. It didn't, and by then couldn't, replace it without tearing the spacecraft apart and adding years to a program already running late by most of a decade. So there was a spacecraft with a known flaw in the one system that has no redundancy, and there were 4 people assigned to ride it, and there was no version of the future in which someone built them a different shield. What NASA did next has been called elegant by some of the engineers who watched it work, and reckless by a man who has spent 20 years arguing that this is precisely how NASA kills its own crews. Both of them are looking at the same test data. In 1957, an astronomer cataloged a faint smudge of light as a star. It was not a star. It was TON 618, 10.5 billion light-years away. For it to look that bright from that distance, something at its center has to be pouring out more light than 140 trillion suns. We now know what? A black hole of 66 billion solar masses. Not million, billion. In a test chamber in California, engineers spent 2 years firing superheated gas at blocks of the same material that would sit beneath 4 astronauts. They were not trying to prove the shield was safe. They were trying to find out what would break it. An arc jet works by pushing gas through an electric arc until it reaches temperatures that reproduce re-entry conditions, then aiming it at a sample. It is the closest thing there is to flying a piece of a heat shield without launching it. You can hold the heating rate steady, or ramp it, or drop it in the middle to imitate a skip. And crucially, you can do it 200 times. That is what produced the finding that reframed the whole problem. Samples with higher permeability came through cleanly. Samples with lower permeability cracked and shed. Change how much the heating rate dipped mid-test, and the damage changed with it. Which meant the char loss was not random. It had a recipe, and the recipe had 2 ingredients. One of those ingredients was the material, and the material could not be changed. It was already installed on a spacecraft in Florida. The other ingredient was the flight path. And a flight path is software, procedures, and arithmetic. You can change it in a room. That is the whole decision. And once you see it that way, it stops looking like a gamble and starts looking like the only move available. Artemis II would not skip. It would come in on a steeper, more direct path, take the heating in one continuous pass rather than two, and keep the heating rate high enough throughout that the outer layer of avocoat stayed properly charred the entire way down. Keep the surface burning hard and the char layer stays permeable. Keep the char layer permeable and the gas escapes. Let the gas escape and nothing builds up underneath. Hotter, deliberately, as a safety measure. Nothing is free. The change cost two things, and NASA said so. The first cost was flexibility. A skip entry lets a capsule stretch or shorten its flight through the atmosphere, which means it can reach for a landing point hundreds of miles away from where it would otherwise come down. That is how you dodge a storm sitting over your recovery zone. Flying steeper shrinks that range considerably. The Artemis II crew would have far less ability to move their splashdown point if the Pacific turned ugly on the day. The second cost was heat. A single continuous pass means the shield never gets the break the skip provides. Total heating goes up, and the structure underneath has to absorb more of it for longer. NASA's position was that this was the point. The higher sustained heating was not a side effect to be tolerated. It was the mechanism. There was a second half to the decision that gets less attention and matters more. For the long run, NASA did not decide that the avocoat problem was solved. It decided that this particular flight could be flown safely with this particular shield, while separately committing to fix the material for later capsules. In effect, char loss was reclassified, not as a defect that had been repaired, but as a known behavior with understood limits, bounded by how the spacecraft flies. Manage it operationally now, engineer it out later. In January of 2026, NASA's administrator, Jared Isaacman, put his name on it. He had come into the job with the flight already scheduled and the argument already public, and he did what a new administrator in that position can do. He sat through briefings with senior leaders and spent half a day reviewing the findings with outside experts. Then, he said he had full confidence in the Orion spacecraft and its heat shield, grounded in rigorous analysis and the work of engineers who had followed the data. That sentence is doing a lot of work, and it is worth reading carefully rather than quickly. Followed the data is a claim about process rather than about outcome. It says the conclusion came from the evidence rather than from the schedule, which is exactly the claim the other side disputed. In the same month, NASA did something agencies under criticism usually do not do. It invited its loudest technical critic into a briefing on the heat shield, along with two journalists, and gave him access to research material that had not been made public. That's genuinely unusual, and people on both sides of this argument have said so. It's the behavior of an organization that believes its analysis will survive contact with a hostile expert. It did not go the way NASA hoped. The critic came out of that briefing more alarmed than he went in and published a long, public, furious response. Not a press statement, something closer to a plea. 11 weeks later, the rocket launched with 4 people on it. Before we go to his argument, one thing has to be said clearly, because the rest of this only makes sense if it is understood. This was not a case of NASA ignoring a problem. NASA found the problem, ran a multi-year investigation, identified a physical mechanism, reproduced it in ground testing, redesigned the flight around it, published the findings, briefed its critics, and flew. Every one of those steps is what a functioning engineering organization does. The disagreement is narrower and sharper than did NASA cut corners. It is this: when you have identified a mechanism you didn't anticipate, and you can't test the actual flight article, and you can't replace it, how confident are you allowed to be that your model of the mechanism is complete? NASA's answer was
confident enough because the ground tests reproduced the behavior and the physics is understood well enough to bound it. The other answer, from a man who had watched 2 space shuttle crews die inside exactly this kind of reasoning, was that a model which reproduces a failure is not the same as a model which predicts one. Charles Camarda flew on Discovery in 2005 on the first mission after Columbia, sitting on top of the same problem NASA had just spent 2 years insisting it had solved. He spent the 20 years since arguing that the agency's real failure mode is not carelessness. It's the confidence that comes from doing the math.
In July of 2005, NASA launched the Space Shuttle Discovery on the first flight after Columbia. The agency had spent 2.5 years and an enormous amount of institutional pain proving that the foam problem was fixed. 81 seconds into the ascent, a piece of foam came off the tank. It missed the orbiter. The crew came home. NASA grounded the fleet again. One of the 7 people on board that flight was a mission specialist named Charles Camarda. He was an engineer by training, not a pilot, with a doctorate and decades at NASA Langley behind him. He rode into orbit on a vehicle the agency had declared repaired and watched it prove otherwise on the way up. 21 years later, he became the most prominent technical voice arguing that NASA should not fly Artemis II. His argument is not the one most people assume. He was not saying NASA was hiding something. He was not saying the engineers were lazy or the managers corrupt. Every version of that claim is easy to make and easy to dismiss, and it is not what he said. He was making a claim about how organizations fool themselves with mathematics. Here is the shape of it. When something fails in a way you did not predict, you have learned that your understanding of the system was incomplete. You then build a new model to explain what happened. That model can be made to reproduce the failure because you built it knowing the answer. Reproducing a result you already have is not the same as being able to predict a result you do not. And a model that fits your existing data can still be wrong about conditions outside the range you tested. That is precisely the region a crew flies through. Camarda's position, as he set it out publicly in early 2026, was that NASA had not established the root cause with the depth that phrase implies. It had established a plausible mechanism, built analysis around it, and treated the analysis as understanding. The reason this landed as hard as it did is that it is the exact diagnosis produced by the 2 worst days in NASA's history. Before Challenger, engineers had watched the booster seals erode on previous flights. Erosion was not supposed to happen at all, but it happened and the crews came home, and it happened again and the crews came home. Each survival became evidence that the condition was acceptable. The sociologist Diane Vaughan later gave it a name that has never stopped being useful: normalization of deviance. The slow process by which a thing you originally called unacceptable becomes, through repeated survival, the way things are. Before Columbia, foam had been coming off the external tank for years. It was categorized as a maintenance issue rather than a flight safety issue because it had never killed anyone yet. Camarda's contention was that char loss was traveling the same road. It had not been predicted. It had happened anyway. Nobody had died because nobody had been on board. And now it was being reclassified as a known, bounded behavior to be managed rather than a defect to be removed. That is the argument. It is not a conspiracy theory. It is a pattern recognition claim from someone who has seen the pattern twice from inside. Now the other side at equal strength because it is not weak. NASA's engineers did not build one model and admire it. They ran a physical test campaign that reproduced the failure repeatedly under controlled conditions and found a variable that governed it. Change the permeability, change the outcome. Change the heating profile, change the outcome. That is not curve fitting. That is identifying a causal lever and demonstrating control over it. They also had a natural experiment sitting in front of them. On the flown Artemis I shield itself, the more permeable regions had come through in better condition than the less permeable ones. The material had, in effect, run the comparison for them at full scale, in flight, at lunar return velocity. And the fix they chose was not a patch on the hardware. It removed the specific condition the mechanism required. No skip, no drop in heating rate, no window in which gas production outran gas escape. If the mechanism is right, the fix eliminates it. If the mechanism is wrong, the fix might do nothing. There is one more argument on NASA's side that rarely gets stated out loud, and it deserves to be. The alternative to flying was not a safer flight. It was a delay of years while a new heat shield was designed, qualified, and installed, during which the program's funding, workforce, and political support would all have been in play. Choosing not to fly is also a decision with consequences, and pretending otherwise is its own kind of dishonesty. So here is the honest verdict, and it is not satisfying. This was genuinely unsettled. Not unsettled in the way that means one side was obviously right and the other was noise. Two sets of qualified people looked at the same test data and reached contradictory conclusions about how much it licensed, and both of them could give you a coherent account of why. What is not in dispute is that nobody could test the actual article. The heat shield that would fly was the heat shield that would fly. It could not be sampled without damaging it, could not be flown twice, and could not be replaced. Everything came down to whether the reasoning was right, and reasoning is not something you can inspect with a camera. The four people on board understood this. They are test pilots and engineers. They had been briefed on all of it, and none of them was under the impression that the argument had been resolved to everyone's satisfaction. Isaacman said something after they came home that is worth holding on to, because it doesn't sound like a victory statement. He said the crew had accepted significant risk in service of the knowledge gained. That's an admission, and it's a fair one. Not the shield was safe, not the critics were wrong. The crew accepted risk on purpose, knowingly, because that's what a test flight is, and because the only way to find out whether the reasoning was right was to fly through it. By the time Camarda's critique was circulating and the flight readiness review was concluding, the argument had already become theoretical. Integrity was 200,000 miles out, accelerating away from every laboratory on Earth, on a path chosen 4 years ago for reasons that had nothing to do with heat shields, and about to deliver something nobody had planned for.
Somewhere in the second day of the mission, Earth stopped being a landscape and became an object. There's a moment on every lunar flight where the planet no longer fills the window, no longer curves away past the edges of the frame, and simply hangs there, whole and finite, and you can hold your thumb up and cover it. 24 people had seen that before this crew, all of them between 1968 and 1972. What is strange about the journey out is how little happens. The upper stage fired once, hard, on the first evening, and after that the engines were essentially done. Everything from that point was coasting, falling, technically, in a long arc away from the planet, slowing continuously the whole way as the planet pulled back. The shape of that arc is the thing worth understanding because it explains almost everything else about this mission, including the record and the eclipse, and the reason NASA had only 7 launch dates. It is called a free return trajectory. You aim the spacecraft not at the moon, but at a point ahead of where the moon will be, so that by the time you arrive, it has moved into position. You pass behind it. Its gravity bends your path around, and the bend is calculated so that what comes out the other side is a curve that leads back to Earth. Draw the whole thing, and it looks like a figure 8, with the Earth in one loop and the moon in the other. The word free is doing the work in that name, not free of charge, free of engines. If everything on the spacecraft failed the moment after that first burn, the crew would still come home, because home is where the path already goes. No decisions required, no propulsion required. The trajectory itself is the abort plan. Which is why the last people to hold the distance record were on Apollo 13. Apollo 13 was not trying to set a record. 55 hours into the flight, an oxygen tank in the service module ruptured. The landing was gone within minutes. What remained was a crippled spacecraft 200,000 miles from Earth, with a lander attached that was never designed to keep 3 people alive. The crew's survival depended on getting back onto a free return path and letting the moon throw them home. That is what carried them around the far side, and incidentally, farther from Earth than any human had been. 248,655 miles. Set by accident in an emergency, by 3 men trying not to die. That record stood for 56 years. And Artemis II broke it by flying, on purpose, the same maneuver Apollo 13 flew as a last resort. On the 3rd of April, the crew passed the halfway point between Earth and the Moon. Halfway in distance, not in time. The spacecraft was still climbing out of Earth's gravity and losing speed the entire way, so the second half of the trip took considerably longer than the first. Meanwhile, the mission was doing its actual job, which was unglamorous and continuous. Every system on Orion was being run, logged, and compared against prediction. Communications at increasing range, thermal control as the spacecraft rotated, radiation monitoring, which matters enormously because beyond the protection of Earth's magnetic field, the dose rate climbs and nobody has good long-duration data on humans out there. They also ate. The menu on the 6th day included vegetarian chili, salmon croquettes, chicken with peanut sauce, pickled beets, barbecue beef brisket, and chocolate pudding, which is a level of variety Apollo crews would have regarded as science fiction. And they talked to people. A downlink press conference on the 2nd day, a call with Canadian school children on the 4th, which was Hansen's assignment as much as anyone's. There was also a call between Integrity and the International Space Station, the first ship-to-ship conversation between a crew in deep space and a crew in low Earth orbit. Now, the thing about the trajectory that nobody planned for. The free return path was chosen for safety. The launch date was where the moon sat in early April. Put those 2 constraints together, and the result was that on the 6th of April, as Integrity swung around the far side, the moon would pass directly between the spacecraft and the sun. From where they were, the moon would cover the sun completely. Victor Glover said afterwards that he was glad they had launched on April 1st, because launching on any other date would have meant not seeing it. That is worth stating precisely because it's the strangest consequence of an engineering decision in this entire story. The heat shield problem shaped the re-entry. The re-entry shaped nothing about the outbound leg. But the free return trajectory, chosen because it is the path that brings you home without engines, delivered the crew into a total solar eclipse that no human being had ever witnessed from that vantage point. Nobody designed that. It fell out of the geometry. By the evening of the 6th, Integrity was closing on the moon at the end of 4 days of falling. Ahead of them was the far side, a surface that no human eye had looked at directly since 1972. Behind them, at a distance now measured in light seconds, was every person alive. And at 6:44 in the evening Eastern Time, Mission Control lost the signal. For the next 41 minutes, there was no way to reach them, and no way for them to reach anyone else. Somewhere inside that silence, Integrity would pass closer to the moon than it would ever again, and 4 people would become the farthest humans in history, with nobody on Earth being able to watch it happen. At 6:44 in the evening on April 6th, 4 people stopped existing as far as the Earth was concerned, not metaphorically. The moon is a solid ball of rock 2,000 miles across, and radio waves do not go through it. When Integrity crossed behind the far side, every antenna on Earth lost the signal at once. No telemetry, no voice, no heartbeat data, no spacecraft status. Nothing. For the next 41 minutes, the four most distant humans in history were also the four most isolated. This is routine. Every Apollo crew went through it. Mission Control knows exactly when the signal will drop and exactly when it will return. And if it returns on schedule, everything is fine. But knowing the arithmetic does not change what the room feels like, because inside that window, there is no version of help. Earlier that afternoon, something had already happened that they could talk about. At 56 minutes past noon Central Time, Integrity passed 248,655 miles from Earth. That is the Apollo 13 number, set in April of 1970 by three men who had never wanted it. 56 years, almost to the week, and it went by like a mile marker. The call came up from Houston. The capsule communicator on shift was Jenny Gibbons, a Canadian astronaut, which meant that at the moment humanity's distance record changed hands. The voice on the loop and one of the people breaking it were both from the same country that had never sent anyone beyond low Earth orbit before. Gibbons told them that they were pushing the frontier for everyone. Hansen answered for the crew, and what he said was not a celebration. He framed it as an inheritance, honoring the people who had gone before them. And then he did something unusual. He said he hoped the record would not last long. Then they went to work, because the flyby was not a sightseeing pass. It was the single most concentrated block of science on the mission, and it ran for about 6 hours. 4 people with cameras and their own eyes looking at terrain that no human being had seen directly since December of 1972. They photographed Reiner Gamma, one of the strangest features on the moon, a bright swirl with no topography, associated with a patch of magnetized crust that nobody fully understands. They looked at Glushko crater. They logged shades of brown and blue in the surface that they had not expected and that carry information about the moon's history. Along the terminator, the boundary between lunar day and night, low-angle sunlight threw shadows across Joule, Birkhoff, and Stebbins craters, which is the lighting geologists want because it turns a flat gray plane into topography. At that range, NASA had said beforehand, the moon would look about the size of a basketball held at arm's length. As they came around, the sunlit crescent of the far side thinned, 20% lit, then less, and in that thinning sliver, they saw Mare Orientale, a vast bullseye of concentric mountain rings punched out by an ancient impact, along with Pierrazzo crater and Ohm crater. No human eye had ever seen them. And then, the crescent closed. From inside Integrity, the moon slid across the sun and covered it completely. On Earth, totality lasts a few minutes at best. You stand in a shadow moving across the ground at 1,000 miles an hour, and it is gone before your eyes have adjusted. From Orion, totality lasted the better part of an hour. The cameras that recorded it were the ones mounted on the solar array wings, installed so engineers could inspect the spacecraft from outside. What they captured is genuinely difficult to describe. The sun's outer atmosphere, the corona, is normally invisible because the sun itself is too bright. Block the disk and the corona appears as a glowing halo, and solar physicists build instruments called coronagraphs specifically to do this. The moon was acting as a coronagraph in space, with no atmosphere in the way to scatter or blur anything. Stars are in those photographs, which almost never happens in spaceflight imagery because everything is usually too bright. Venus is in one of them. In the official flyby image released later, Saturn sits just below the moon's lower right edge, and Mars is at the frame's right edge. And along one edge of the black lunar disk was a faint glow, which was sunlight that had bounced off Earth, crossed 250,000 miles, and landed on the moon's near side. Glover described the moment the sun went behind the moon and Earthshine appeared. He later said the whole thing felt like they had gone sci-fi. He also said plainly that he hoped that they had launched on April 1st,
because launching on any other day would have meant not seeing it at all. Inside the radio blackout, two things happened about 2 minutes apart. At 6 seconds before 7 o'clock, Integrity reached its closest approach to the moon, about 4,067 miles above the surface. And at 2 minutes and 51 seconds past 7, the spacecraft reached its farthest point from Earth, 252,756 miles. Nobody on Earth watched it happen. Nobody could. At 25 minutes past 7, the signal came back. Now the payoff, and it is not the number itself. The record had almost nothing to do with the rocket. The Saturn V was more powerful than the Space Launch System. Apollo 11 did not go as far as Artemis II, and neither did any of the missions that actually landed, because a landing mission wants a close, tight orbit, and a flyby wants a wide, sweeping arc. What set the record was where the moon happened to be. The moon's orbit is not a circle. At its farthest, it sits about 25,000 miles beyond its closest. And on April 6, 2026, it was near the far end of that range. Add a trajectory that swings wide behind it rather than breaking into orbit, and the arithmetic does the rest. The margin over Apollo 13 was 4,101 miles, slightly more than the radius of the Earth. 56 years of spaceflight, and the human frontier moved outward by about half the width of the planet we left. There's one more thing Reed Wiseman did as the record fell, and it was not in any procedure. He asked that a crater on the moon be given a name, and the name was not his own.
At the 10 o'clock position of the Oriental Basin, on a piece of the moon that no human had looked at before that afternoon, there are two small craters sitting close together. They had no names. Most of the far side is like that. There are hundreds of thousands of craters on the moon, and only a fraction of them carry names. And the ones that do were mostly assigned from photographs by committees to honor scientists and explorers who never saw them. Artemis II suggested two names for those two craters: Integrity for the spacecraft they were sitting in, and Carol. Carol was Reed Wiseman's wife. She died of cancer in 2020, 3 years after he had been flying as an astronaut, and 3 years before he was named to command this mission. There is nothing to add to that, and the film should not try. He commanded the first crewed flight beyond low Earth orbit in 53 years, and while he was farther from Earth than anyone had ever been, he asked that a piece of the moon carry her name. Whether it sticks is not up to NASA. Lunar feature names are approved by the International Astronomical Union, which has its own rules, its own conventions, and its own timeline. What the crew did was propose. The word in the record is suggested. Some crew suggestions have become official. Apollo astronauts named landmarks on the fly during their missions, and a number of those informal names were later ratified. Others never were, and the moon is scattered with places that have a name only in the transcripts. Now from that to a toilet. Because this is a test flight, and a test flight is an inventory of everything that did not work exactly as designed, and the item on that list that generated the most discussion was the waste management system. Orion's toilet routes liquid waste through a vent line that dumps it overboard. In vacuum, at the temperatures outside a spacecraft, urine leaving a narrow pipe does not simply disperse, it freezes. And frozen urine accumulating in a vent line eventually blocks it. That is what happened. And it was not a one-off. It was a recurring problem across the mission, significant enough that NASA opened a formal post-flight investigation into it, and significant enough that when the capsule came back, engineers listed the toilet alongside the heat shield as hardware requiring examination. It sounds like a joke. It is not, and it's worth explaining why. Artemis II lasted 9 days. The missions this flight exists to enable last considerably longer, with crews going to the lunar surface and staying. A waste system that clogs intermittently over 9 days is an inconvenience.
The same system over 30 days, with no resupply and no way home in under 3 days, is a mission-ending failure. There is history here. Apollo's waste management was, by every crew account, miserable. Bags, adhesive seals, manual handling, and results that made the cabin unpleasant for a week. It was tolerated because Apollo missions were short and because nobody had a better answer. Half a century later, a spacecraft designed for months of deep space operation still had a plumbing problem that ice could defeat. This is what test flights are for. Nobody would have found it in a simulator because a simulator does not have vacuum on the other side of the wall. The toilet was one item on a much longer list, and most of the list was quieter. Life support ran for 9 days with 4 people breathing. Thermal control held while the spacecraft rotated to manage sunlight. Communications worked out to 250,000 miles and back. Radiation instruments logged the dose the crew absorbed beyond the protection of Earth's magnetic field, which is the number that matters most for any mission longer than this one. None of that produces a headline. All of it is the reason the flight happened. On the way out from the moon, Wiseman photographed Earth setting behind the lunar limb. Apollo 8 took the photograph that image is talking to. Earthrise, Christmas Eve 1968, the planet coming up over the lunar horizon in color, which more than one person has argued did more for the environmental movement than any argument ever made. 57 years later, the same view going the other way. And here is what the numbers do to that image, which is the thing this chapter has been walking toward. 252,000 miles sounds enormous, and in every sense that matters to the universe, it's nothing. Light crosses it in about 1 1/3 seconds. The sun is roughly 370 times farther away. The nearest star beyond it is about 100 million times farther. The farthest any human being has ever been from home is a distance light covers while you finish saying the word, which is the honest scale of this achievement, and it does not diminish it. 4 people went to a place where the entire planet fits behind a raised thumb, spent 6 hours looking at ground nobody had ever seen, watched the sun disappear for the better part of an hour, and asked that 2 unnamed craters be called Integrity and Carol. And then they had to come back. If you want the rest of the Artemis story, the mission that follows this one and the landing after that, that film is linked below. The journey home took 3.5 days, and for almost all of it, there was nothing to do but fall. Falling toward Earth is the opposite of the trip out. On the way to the moon, the spacecraft slowed continuously. On the way back, it accelerated continuously, gaining speed for 84 hours, until by the end, it was moving faster than any object carrying human beings had in 56 years. And all of that speed had to go somewhere. There are only 2 ways to slow down a spacecraft. You can fire an engine, which requires carrying enough propellant to undo everything the launch did, and no vehicle has ever been built that could. Or you can hit the atmosphere and convert the entire thing into heat, and hope that the argument about the heat shield was right. A spacecraft coming home from the moon has a problem that has nothing to do with heat shields and everything to do with arithmetic. It is carrying an enormous amount of energy, and there is nowhere to put it. The launch spent millions of pounds of thrust getting the vehicle up to speed. Coming back, all of that has to be removed. Every mile per hour the rocket gave it has to be taken away again before it touches the ocean. You could do it with engines. In principle, you fire retro rockets and slow down gently and land like a spacecraft in a 1950s film. In practice, that requires carrying roughly as much propellant for the stopping as you carried for the starting, all the way to the moon and back, which means launching a far bigger rocket to carry it, which requires more propellant to stop that, and the arithmetic runs away from you before you get anywhere near a design that closes. So every crewed spacecraft ever flown has done the other thing. It throws itself at the air and converts the energy into heat. Roughly 25,000 miles an hour down to about 20 in a quarter of an hour, using nothing but atmosphere. And there is a corridor you have to fly through.
and it is narrower than most people imagine. Come in too shallow, and the atmosphere will not grab you. You skip off the top like a stone and go back out into space on a long orbit, and depending on your consumables, that is a very bad afternoon. Come in too steep, and you decelerate so hard that the heating exceeds what the shield can carry, and the loads exceed what the crew can survive. The window between those two outcomes for a lunar return is a matter of a degree or two of flight path angle. Artemis II had flown the shallow end of that corridor on purpose, using the skip. The skip is a genuinely good idea, and it deserves defending, because this film has spent 5 chapters treating it as the villain. Dip into the atmosphere, bleed off a chunk of speed, rise back into thin air where the heating drops, then come down again for the final descent. It does 2 useful things. It splits the heat load into 2 smaller doses instead of 1 large one. And because you can control how long the skip lasts, you can stretch or shorten your flight and choose where you land with considerable precision. Apollo used skip entries. They worked. The problem was in the trough. Up in the thin part between the 2 dips, the heating rate fell. Surface charring slowed down, but the material underneath was still hot, still breaking down, still producing gas. Gas production stayed high while the surface stopped renewing the permeable char layer that lets gas escape. Pressure built in the exact window where the shield appeared from the outside to be having the easiest time of the whole descent. So Artemis II did not skip. 1 continuous pass, steeper flight path angle, in and down, no rise, no trough, no pause. And critically, the heating rate stayed high the whole way through, rather than falling away in the middle. That is the fix, and stated plainly, it sounds like the opposite of a safety measure. NASA made the re-entry hotter and kept it hotter for longer, and that was the point. Because if the surface keeps burning hard, the char layer keeps renewing, and a freshly charred layer is a permeable one. Gas gets out as fast as it's made. Nothing accumulates, nothing cracks. Keep the fire going, and the material behaves. Let it cool in the middle, and it fails. There's a version of this that's easy to sneer at, and it goes, NASA couldn't fix the hardware, so it changed the paperwork. That's not what happened, and the difference matters. The trajectory was chosen to eliminate the specific physical condition the failure required. The failure needed a heating trough. The new profile has no heating trough. If the diagnosis was correct, the failure mode is not reduced, it is absent. That's a real engineering fix. It's also, and this is the whole tension of the film, a fix that's only as good as the diagnosis underneath it. And it costs something real. The skip is what gives a capsule the ability to reach for a landing point far from where it would otherwise fall. Removing it shrank that range considerably. If a storm had parked itself over the recovery zone off San Diego on the 10th of April, the Artemis II crew would have had far less room to move their splashdown point than a skip entry would have given them. NASA accepted a narrower weather margin in exchange for a heating profile it believed in. That's a trade, made openly, with the reasoning published. The second cost was simply more heat. A single continuous pass means the structure absorbs more total energy than it would have in 2 smaller doses. The shield had to carry it, and so did everything behind the shield. By the afternoon of April 10th, all of this had stopped being an argument. The trajectory was set, the service module would be jettisoned, the capsule would turn blunt end forward and hold that attitude, and there would be no further decisions available to anyone, on the spacecraft or on the ground. Every model had been run, every ArcJet test had been fired, every review board had voted. 2 years of investigation, 3 months of public argument, and 1 administrator's signature had all converged on a single prediction about how a piece of material would behave for about 10 minutes. Nobody could inspect it. Nobody could test it. Nobody could change it. At 7:53 in the evening Eastern Time, integrity touched the top of the atmosphere at nearly 25,000 miles an hour. 4 minutes later, the radio went silent again, for the second time in 4 days. And this time, nobody on Earth knew whether the silence would end.
The first thing that happens is that half the spacecraft leaves.
The European service module, which had carried the propellant and the oxygen and the water and the power for 9 days, which held the engine that had shaped the entire trajectory, separates and is discarded. It will burn up in the atmosphere on its own, in pieces, with nobody watching. Everything the crew has left is inside a cone 16.5 feet across at its base. The capsule rotates until the heat shield faces the direction of travel. That attitude is not a preference. It is the only survivable orientation, and holding it is the single most important thing the guidance system does for the next quarter of an hour. At 7:53 in the evening, Eastern Time, Integrity reached entry interface, the altitude where the atmosphere begins to matter, about 400,000 feet. Nothing dramatic happens at first. The air is so thin it is barely air. Then, within seconds, the glow appears at the edges of the shield and starts to spread. The capsule is not burning, the air in front of it is. Almost everyone believes re-entry heat comes from friction, from a spacecraft rubbing against the atmosphere. It does not. At this speed, the vehicle cannot push the air out of its way fast enough, so the gas piles up in a compressed layer in front of the blunt face. Squeeze it gas hard enough and it gets hot. Squeeze it this hard and it stops behaving like a gas at all, tearing apart into charged particles, glowing. That glowing sheath is plasma, and it is the reason the shape matters. A pointed nose would slice into the air and drag the shock layer down onto the skin. A blunt one holds it standing off in front, keeping the worst of the heat in the gas rather than in the vehicle. Around 5,000 degrees Fahrenheit, and the shield begins spending itself. The outer layer chars, breaks down, turns partly to gas, and streams away behind the capsule, carrying heat with it. This is the process that failed on Artemis I. This is the process NASA had reshaped the descent to protect. Then the radio went out. Plasma does not let radio through. The same charged sheath that is carrying away the heat also wraps the spacecraft in a shell that blocks the signal, and for several minutes there is no telemetry and no voice, exactly as there had been 4 days earlier behind the moon. The difference is that the blackout behind the moon was geometry. Everyone knew when it would end because the moon's position could be calculated to the second. This blackout ends when the spacecraft has slowed enough for the plasma to thin, which depends on how the descent is going. Somewhere inside that silence, the capsule passed through peak heating. NASA's flight dynamics team had estimated the maximum velocity during re-entry at 24,661 miles an hour, reached at about 7:54, right at the start of the blackout. That is roughly 130 miles an hour short of the fastest a crewed vehicle has ever traveled, a record Apollo 10 set in 1969 and still holds. The crew, meanwhile, were being pressed into their seats at close to 4 times their own weight after 9 days in weightlessness. That combination is genuinely hard on a body. And then the glow faded and the signal came back. Rob Navius, the NASA commentator working the descent, said it was a perfect descent for Integrity and that the crew sounded hale and hearty on board. What follows is a sequence with no room in it for error. The forward bay cover comes off the top of the capsule, pulled away by its own small mortars. Then 2 drogue parachutes deploy, small and strong, and their job is not to stop the capsule, but to stabilize it and slow it enough that the main parachutes wouldn't tear. Then 3 mains. Orange and white, enormous, filling one after another. The capsule goes from falling to descending. By the last stage, it was moving at about 20 miles an hour, slower than city traffic. Conditions on the water were unremarkable, which is exactly what everyone wanted given the reduced weather margin the trajectory change had cost. Scattered cloud, winds around 10 knots, wave heights of roughly 4 feet, comfortably inside the limits. At 7 minutes past 8 in the evening Eastern Time, 5 minutes past 5 in the afternoon in California,
Integrity hit the Pacific off the coast of San Diego. 9 days, 1 hour, and 32 minutes after leaving Florida. Now the two numbers that answer the question this film has been carrying since its first sentence. Orion splashed down 2.9 miles from its targeted landing site, and the velocity at entry interface, the speed at which the capsule met the atmosphere, was within 1 mile per hour of what had been predicted. Read those together, because separately they're trivia, and together they're the whole argument. The models NASA used to design that re-entry predicted where the spacecraft would be, how fast it would be going, and where it would land. And reality came in within 1 mile per hour and under 3 miles, on a return from 250,000 miles away, on a trajectory that had been redesigned specifically to manage a material failure nobody had anticipated. The models were not fitting a curve after the fact. They were predicting in advance, and the prediction held. About an hour after splashdown, Navy divers brought all 4 crew members out onto an inflatable platform called the front porch. Wiseman reported everyone in excellent shape. Helicopters lifted them one at a time to the USS John P. Murtha for medical evaluation, and as the first of them approached the ship, a call went out across the deck. Integrity, incoming. Everything up to this point proves the crew survived. It does not prove the heat shield was fine, and those are different claims. While the crew were being flown to the ship, divers were already in the water underneath the capsule with cameras, photographing the one surface nobody had been able to inspect for 3 years.
The first look at the most argued about object in American spaceflight came from a diver holding a camera in the dark. Within minutes of splashdown, Navy divers were in the water underneath Integrity photographing the heat shield. Not for the archive, for the engineers, who had spent 3 years unable to see this surface and now had about an hour before the capsule was hoisted aboard. What they photographed was a surface that had eroded. That is the correct outcome, and it is worth saying clearly one more time. A pristine shield would have meant the heat went into the spacecraft. What matters is how it eroded, and the comparison to Artemis I is not subtle. Where the first shield had cavities and cracks and material missing in chunks, this one had charred. NASA's language, after divers and then teams aboard the ship had looked at it, was that the char loss behavior observed on Artemis I was significantly reduced, both in quantity and size. Initial inspections found the system performed as expected, with no unusual conditions identified. The next day, in the well deck of the Murtha, the 4 astronauts went down and looked at it themselves, alongside NASA engineers and a flight surgeon. Wiseman's assessment afterward was that to 4 humans just looking at it, the shield looked wonderful, and he was careful to add that instrument-level analysis still had to confirm what the photographs suggested. He noted minor charring near the shoulder, the junction where the heat shield meets the side of the capsule. Elsewhere, the news was quietly remarkable. The ceramic tiles on the upper conical back shell performed as expected, and reflective thermal tape, which is used to control the vehicle's temperature in space and is fully expected to burn off during re-entry, was still present in numerous places. Material that was supposed to be gone was still there. Then a photograph went around the internet and people saw a missing patch. It looked like a section of the shield had come away. Given 3 years of headlines about char loss, the reading was understandable and it spread fast. It was a compression pad. Orion's heat shield has them. They are documented in NASA's own technical material on the spacecraft's thermal protection, and under certain lighting and camera angles, they appear as pale or discolored spots against the darker avcot. Isaacman addressed it directly and unusually quickly for an agency administrator. He said no unexpected conditions had been observed, and that the discoloration was not liberated material, meaning nothing had come off. He identified the area as the compression pad region and said it matched what engineers had seen in pre-flight testing. He also said he was hesitant to get ahead of a proper data review, but that he understood the space community's curiosity, especially when an image can give the impression of a problem. And there was a detail in the early assessment that mattered more than the photograph.
NASA reported that the shield's performance was consistent with the ArcJet ground testing conducted after Artemis I. The tests predicted a behavior. The flight produced that behavior. That is the strongest single piece of evidence in favor of the diagnosis being correct, and it is a considerably better result than simply surviving. So the case is closed. Except NASA did not close it. 3 separate lines of investigation continued past splashdown. Airborne imagery captured during the descent went for review, specifically to establish the timing of when the minimal char loss occurred, which tells engineers which part of the descent produced it. The crew module went back to Kennedy for detailed inspection during deservicing, and over the summer, the heat shield itself was to be transported to Marshall Space Center in Huntsville, Alabama, for sample extraction and internal X-ray scans. Read that phrase carefully: internal scans. The photographs show the outside. The entire failure mechanism on Artemis I happened on the inside, underneath the char layer, where gas built up and pressure accumulated, and nobody could see any of it until pieces came off. A shield can look correct on the surface and still have done something unexpected 2 millimeters down. That is why the investigation continued after a splashdown that matched the plan to within 1 mile per hour. Not because NASA doubted the crew were safe, because looking at a surface tells you what happened at the surface, and the argument was never about the surface. Those scans were scheduled for the summer of 2026. As of the making of this film, NASA has not published their results, which means the honest state of this story is that the flight succeeded, the crew came home, the predictions held, the surface looked far better than anyone had reason to fear, and the deepest question anyone asked about the material has not yet been answered in public. It is worth being precise about what this does and does not settle regarding the argument earlier in this film. It settles a great deal. The mechanism NASA identified predicted an outcome. The outcome occurred. The fix removed the condition the failure required, and the failure was substantially absent. That is not luck, and anyone claiming otherwise has to explain how a wrong model produced a right prediction across a 14-minute descent from 1/4 mile million. It does not settle everything. One flight is one data point. The critique was never that the shield would certainly fail. It was that the confidence was not warranted by the evidence. A single success does not retroactively make an argument sound, in the same way that surviving a foam strike did not make foam shedding acceptable. And NASA has behaved as though it agrees. It flew this shield while separately committing to change the material for later capsules. Both halves of that were always the plan. The most accurate summary is that the risk was managed rather than eliminated, that the management worked, and that the elimination is still being engineered. Everything Artemis II proved was in service of what comes next, and what comes next turned out not to be what almost anyone expected. 2 months after splashdown, NASA announced the crew of the following mission, and that crew is not going to the moon.
On the 9th of June, 2026, 2 months after Integrity came out of the Pacific, NASA introduced the crew of Artemis III. Randy Bresnik commanding, Luca Parmitano as pilot, Frank Rubio and Andre Douglas as mission specialists, with Bob Hines named as backup. Parmitano flies for the European Space Agency, and this is the first time an ESA astronaut has been assigned to an Artemis mission at all. Rubio holds the American record for the longest single spaceflight, 371 days aboard the International Space Station, most of it unplanned. And Artemis III is not going to the moon. The mission, targeted for 2027, will launch on the Space Launch System, put Orion in low Earth orbit, and then do something Orion has never done. It will rendezvous and dock with test versions of the commercial landers being built by Blue Origin and SpaceX. One of them, or both. Roughly 2 weeks in orbit, a few hundred miles up, practicing the one maneuver on which everything downstream depends. The landing moved to Artemis IV, the first planned crewed mission to the lunar South Pole, targeted for 2028. Which means that as of this film, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen are the only human beings who have traveled to the moon this century. And
and the next crew to do it has not been named. That reordering looks like a retreat, and it is not quite. It is an admission about where the difficulty actually sits. Under the current plan, no Orion lands on anything. Orion carries the crew out and brings them home, and a separate vehicle does the landing. That vehicle has to be launched separately, and in the case of the SpaceX design, it has to be refueled in orbit by a series of additional launches before it can leave for the moon at all. Propellant transfer between two large vehicles in space at scale is a thing that has been demonstrated in low Earth orbit and has never been done as part of an operational crewed mission. The rocket and the capsule are the mature part of this architecture. The landers are not, which puts that hour of hand flying against a dead rocket stage in a different light. That demonstration was not a curiosity. It was the first data point in the exact capability Artemis II exists to prove, and it happened 4 days into a mission whose headline was a distance record. So what did those 9 days actually buy? They bought a spacecraft with a flight record. Before April, Orion had never carried a person, its life support had never breathed for a crew, and its heat shield had 1 flight and a controversy. Now, the life support has run for 9 days with 4 people. The communications have worked at a quarter of a mile. The guidance has landed within 3 miles of a target after a redesigned re-entry, and the thermal protection has behaved the way the ground tests said it would. They bought a partial answer to the argument, not a complete one. They bought data on what 9 days beyond the magnetic field does to 4 human bodies, which is the number every longer mission is built on. And they bought a list of things that do not work well enough yet, which is what a test flight is for. An ice-up toilet over 9 days is a problem you want to find on the mission with a 3-day ride home, not on the one that stays a month. They also bought something that is not on any requirements document. 4 people looked at Mare Oriental and Pirazzo and Ohm with their own eyes, and no human had ever done that. They watched the sun disappear behind the moon for the better part of an hour and photographed the corona with Saturn and Mars in the same frame. They saw Earth set behind the lunar limb, 57 years after Apollo 8 photographed it rising. And they asked did the 2 craters carry the names Integrity and Carol. Here is the frame this film wants you to leave with, and it's not the triumphant one. The farthest human beings have ever traveled from home is 252,756 miles. The previous record was set 56 years ago, by accident, by a crew trying to survive. The margin between them is 4,101 miles, slightly more than the radius of the planet. Light crosses that entire distance in about 1 1/3 seconds. On the scale of the solar system, it doesn't register. The sun is hundreds of times farther. Voyager 1, launched in 1977 with less computing power than a modern doorbell, is now more than 600 times farther out than any human has ever been. And it got there by doing nothing but continuing. That is not a diminishment. It is the actual shape of the thing. Getting 4 people 1 moon distance from home and back required a rocket producing 8.8 million pounds of thrust, a spacecraft built across 3 continents, a trajectory chosen so that gravity alone would return them if everything failed, and a 2-year argument about whether a single layer of charring epoxy could be trusted with their lives. Which is why the most interesting thing anyone said during the whole mission was said by Jeremy Hansen at the moment the record fell. He did not celebrate it. He said the crew were choosing that moment to challenge this generation and the next to make sure the record was not long-lived. A record you're actively hoping somebody breaks is not a trophy. It's a marker left at the edge of where people have been, with a note attached asking the next ones to move it. 56 years passed between Apollo 13's accidental record and the crew that broke it on purpose. Whether the next gap is 2 years or another 50 depends almost entirely on whether 2 commercial landers work.
and nobody currently knows the answer to that.
The record that Artemis II broke was a set by 3 men who did not want it. On the 11th of April 1970, Jim Lovell, Jack Swigert, and Fred Hayes left Florida intending to land on the moon. 55 hours later, about 200,000 miles out, an oxygen tank in their service module ruptured, and within minutes, the landing was gone, and the question changed from where they would walk to whether they would live. What saved them was the same piece of physics that carried integrity 56 years later. They put the spacecraft back onto a free return trajectory and let the moon's gravity throw them home, because there was no engine they could trust and no other path that ended at Earth. Swinging wide around the far side on a path nobody had designed, they went farther from Earth than any human had ever been. 248,665 miles. Nobody in that spacecraft noticed. They were rationing water, building a carbon dioxide filter out of a flight plan cover and duct tape, and calculating a burn by hand with the Earth in the window as their only alignment reference. The record was an accident of a bad day. 56 years later, 4 people flew almost exactly the same maneuver on purpose in a spacecraft with a heat shield nobody could replace, and moved that marker outward by about the radius of the Earth. They chose to do it. That is the difference, and it is the only one that matters. Which raises a question this film has not answered. Apollo 13 is remembered as the successful failure, the flight that went wrong and came home anyway. That story is usually told as a triumph of improvisation, and it was. But almost everything that saved that crew had been argued about, tested, and rejected years before anyone needed it, by engineers who were told they were being paranoid. The 3 men in that capsule survived on decisions made by people who never flew. That story is the next film.